Hey everybody, this is OC here for another guided note session on how to write and name inorganic compounds, because that can be a little troublesome at some time. So OC wants to help you out if you're having a little bit of trouble from what you read and things like that. Okay, again, I always put the disclaimer that this is a good overview. It's not going to be nitpicky and do everything for you. So definitely make sure after you've gone through this, you go back through your reading and check things out. If you want to write or name inorganic compounds, I guess the first problem you have to have is, what the heck is an inorganic compound? Because that's a really good question. And if you can't tell that right away, you have some issues, because there's different rules if it's inorganic as opposed to molecular. Okay? So generally speaking, if it's an inorganic compound, they generally have a metal in them. Okay, and that metal's bonded with some anion that is a nonmetal. It could be a polyatomic ion for an anion. By the way, there are a few positive polyatomic ions, cations, like ammonium. But pretty much, if you see a polyatomic ion like nitrate, phosphate, carbonate, the ones that you see on that list that I've given you, then you know you have an inorganic compound most likely. Okay, so for instance, if I wrote a compound formula like NaI, is that inorganic? Well, we always write our cations first. So our cation here must be Na. Okay, there's only two elements here, so I have to have an anion and a cation. Remember, inorganic compounds are a cation and an anion. Okay, so if that's true, well, all right, well then we always write our cation first and our anion second. That's tradition. That's what we do. So if that's true, well then Na is my cation and I is my anion. Well, Na, is that a metal or a non-metal? Well, if I think about the periodic table, which I'm going to really horribly sketch here, okay, if I think about the periodic table here, I know that pretty much everything over here and over here are all metals. We know that everything to the right of that staircase is non-metals. And then we have these metalloids here, okay? These weird guys. Semiconductors, we call them, all right? So Na is over here. It's in the metal section. So I have a metal. I have an inorganic compound, okay? What if I had CaI2? Well, again, calcium's over in the metal section. Well, it must be an inorganic compound because calcium's a metal. What if I had Wo2, tungsten, and oxygen? Well, that's oxide to be exact. But if I have tungsten, tungsten's a metal. Where? Why? Because it's in the middle down on the bottom. It's in the metal section. Inorganic. Okay. What if I had SO2? Where's S at? Well, S is in the non-metal section. Well, that's not going to help out. How about O? Is O a metal? No, O is a non-metal as well. This is not an inorganic compound. We would not use what I'm about to show you to name that. You would go to another video and look up molecular compounds. If it's only non-metals, with the one exception being ammonium. Ammonium is a special inorganic NH4+. You see NH4, that's a polyatomic cation. If it's only non-metals, it's a molecular naming system. It could even be an organic naming system if it's carbon-based. Okay, so moleculars, that's a whole nother thing. Okay, we're doing inorganics here. Right? All right, so what if I have a binary inorganic compound? Binary meaning there's just two elements, one cation, one anion, no polyatomics. Okay, so for instance, let's say I'm given a compound like Beryllium Oxide. Okay. All right. Well, beryllium, we always write our cation first. So beryllium is Be. Beryllium is in group 2. All group 2 metals. All group 2 metals. All. No exception. Not a single bit of an exception. Are +2, okay, in their charge when they're cations, okay? So this Be has a 2+ charge, okay? Oxide, O, 2-, because all group 16, ooh, that's a 6, group 16 nonmetals, all are negative 2, all. Okay? This is where we then do our least common multiple, 2, because least common multiple between 2 and 2 is 2. So that means I need a charge of 2 plus from all my berylliums and a charge of 2 minus from all my oxides. So beryllium, to get 1 2 plus charge. So I need a 2 plus because my least common multiple, that's like if I'm putting these two things together, that's a similar charge I need from each to make them even out, to make a neutral charge. Because we have to have neutral charges because compounds, compounds and things don't have charges, okay? I'm not getting shocked by this pen. I'm not going, oh, because it's got a charge, okay? So beryllium, in order to have a non-charged compound with oxide, it's going to have just one of it, Be. Because that would be 2 plus. And oxide, I would just need 1 oxide because I would need 1 2 minus. Okay? So BeO. Right? Well, how would I name a compound? What if I had a compound like CaI2? Okay. Well, calcium is a group 2 metal, so it's only got 1 charge. So all I do is just name it, calcium. Okay. Now, I just name my anion now. According to this, I take my non-metal ion and change its ending to "ide." So this right here is iodine. And "ine" is its ending, so I'm going to go, woo, later. And I'm going to put "ide" on the end of that. So this becomes iodide. All right, iodide. Yeah. All right. Well, what if it was, let's do rubidium. So RB2S. What if I want to name that? You got, see, I think, your hit. It's going to be so hard. No, not really. Rubidium's in group 1, so it's got 1 possible charge. All group 1s are plus 1. That's just the way they are. So I just name my cation, rubidium. Rubidium. And then I name this. Sulfur can be in the pain in the butt because sulfur changes its ending from time to time. But it does get "ide" here. So this becomes sulfide. Take the off and put "ide." So rubidium sulfide. That's how you name binary inorganic compounds. Cation, anion, change the anion to IDE. And the metal ion only has 1 possible charge in these cases. Okay. Wait. What if it has more than 1 possible charge? Because I know those transition metals, those things can have lots of different charges. Like iron. I've looked iron up. Man, there's sometimes iron's 2 plus, there's sometimes iron's 3 plus. Holy gosh, how do I write the name when it's like that? Oh, man. This is cake time. Don't get scared. You got this. Okay? So let me show you. Let's say I have a compound of Fe 2S3. Uh-oh. What do I name this? Some of you might say, well, I'm going to go backwards. I'll go write the formulas of sulfide with these two guys and figure out which one it is and just name it based on that. Get out of here, man. You don't need that. It's logic. Use logic. Don't use memorization. Memorization's not going to help you out. Some of you, on quizzes, things like that, I tend to watch out. I try to get you if you're just memorizing. All we want to do when there's more than 1 possible charge is the Roman numeral. There's a Roman numeral after the metal ion. The Roman numeral represents the charge of that metal. Okay? So this iron right here would be called iron 2 because it's a 2 plus. This iron here is called iron 3 because it's 3 plus. It doesn't tell you how many there are. It just tells you the charge on it. That's it. That's it. Oh my gosh. Okay. So how can I use that to help me out? Well, think oxidation numbers. Oxidation numbers are just charges. And we know that all compounds must add up to a 0. We just talked about that. Compounds have a 0 oxidation number, a 0 charge, because they're neutral. So we can think kind of mathematically here. Reason it out. you know that the sum of all the anion charges, all the negative charges, plus all the cation, all the positive ones, all of them have to add up so you have a 0 overall charge. It's neutral. Well, what do I know? Well, there's some rules you could always follow. For instance, fluorine, if it's in a compound, it's -1. Okay? Fluorine in a compound is going to be fluoride. It's going to be -1 because it's the most electronegative of all elements. Oxygen, in almost all cases, is a -2. The only time it isn't is if it's with fluorine. Duh, because fluorine is always -1. Always -1. The only other time oxygen wouldn't be -2 if it's in a peroxide, and that's when the peroxide itself is a polyatomic ion, and each oxygen has a -1. Okay? That's it. And they're kind of easy to identify because they're not normal looking, sort of. Okay? So we'll take a look maybe one or two later. Okay? So you could go by that. All right? Other than those two basic rules, know that hydrogen is +1 unless it's with an active group 1 or group 2 metal. Okay? In which then it's -1. Right? So hydrogen's +1 if it's with nonmetals, -1 with metals essentially. Okay? Know that group 1 and 2s, oop, I did 2s there. 1 and 2s form their most common charges. Group 1s form +1, group 2s form +2. All right. So know those things, and you're gonna be a-okay. And then you could always pretty much know that in the case of any other barring rule, the most electronegative atom gets its most common charge. So, like if you had a compound of iron and chloride, well, chlorine is more electronegative. It's going to get -1, okay, because it's the more electronegative one, okay. And I might have to use that rule right here, in fact, okay. So, if you want to figure out what the charge is here, well, I know I have 3 sulfurs of some charge, sulfides, and I have 2 irons of some charge. And they got to add up to 0. They got to add up to 0. All right, so you just go down your oxidation rules. Do I have fluorine? I have an F. Oh, but that's iron. That's not fluorine. That's not going to help. Oxygen. Darn it, no oxygen. Hydrogen. Oh, no oxygen. Any group 1 or 2 metals. I got a metal. Oh, it's not group 1 or 2. Dang it. So I just go down with the most electronegative atom gets its charge. Sulfur, on the periodic table, remember that the more electronegative guys are up here. Lower electronegativities. Lower electronegativities. You get more electronegative up that way. Okay. So sulfur, or sulfide in this case, is going to be our more electronegative one. So sulfide being group 2, group 16 nonmetal is going to be a -2. So now all I have to do is kind of solve iron here. Well, this is going to be -6. So 2 times something plus -6 must equal 0. So X must be +3, which means this iron is the iron 3+. So this is iron 3 sulfide. All right. Iron 3 sulfide. All right. All right. So let's squeeze another one in here real quick. Let's try to do one. Let's say we have lead. No, let's do SnF4. SnF4. Right? SnF4. Well, you could look up and realize tin. Oh, crap. Tin can be 2+. Tin could be 4+. Oh, man. Which one is this? Some of you might be real smart and see it right away. I'm going to go a long way because we want to think logically here, folks. Okay? Because remember, the logic never fails. The memorization can fail you. So let's not memorize. Let's just do what we just did. All right. So I know fluoride. Okay. Fluoride's a -1. And because of oxidation rules, it's always -1. No exception. Okay? So let's just set up the idea here. I know that 1 tin plus, so tin's charge, plus 4 times, well, fluoride's always -1, must add up to 0. Right? So that's -4 equals 0 plus X over here. So that means tin's 4 plus. So that means that this compound is tin fo. Tin fo in parentheses. Fluoride. Fluoride. Okay? That's how it works every time, folks. You'll never fail with that idea. Some cool things about oxidation numbers is you can find oxidation numbers inside polyatomic ions, just like if you had a polyatomic ion like nitrate. When you do the sum now, the sum would equal -1. The sum equals the charge on the oxidation number. So kind of remember that. So what if I have polyatomic ions? Okay. Well, polyatomic ion names are kind of weird, so I guess we should really look at those first. Okay. Real quick, a lot of books give you the chlorate one and chlorite one. Woo! ClO3 negative, ClO4 negative, ClO2 negative, and ClO negative. You might say, how the heck do these things have different number of oxygens but have the same charge? It goes back to oxidation numbers, and it goes back to the fact that chlorine is going to change its oxidation number, and that more on that later. Don't worry, okay? The key thing to know when we name these things is that the ATE ending one goes to the most common polyatomic ion of the set. It's not always a 3. Like in this one, it's this one. People are like, oh, it's always the 3 that has it. No, it's the most common one. So chlorate is the most common, and it's the 3 one. For sulfur and oxygen, it's SO4. Okay? And most sheets give you the most common one. And you're going to use them enough that you'll notice which ones are the most common. So this is chlorate. Anytime we look at the polyatomic ion that has 1 less oxygen, we change that 8 to an ite. Every time. I don't care what polyatomic oxyanion we're dealing with. An oxyanion just means a polyatomic with oxygen. Okay, so this is going to be chlorite. Right? So remember, this is sulfate. So 1 less oxygen than it, SO3. 2 minus. Well, that 8 turns into ite. So that's sulfite. And that works that way anytime. If I add CO3 to negative, that's carbonate. How'd I know that? That's one we look up. Carbonate is our most common form of carbon and oxygen in an ion. So that means when I have CO2 to negative, what would that name be? Think. I know you can do it. Yeah, you do something with that 8. Yeah, you just change it to ite. That's it. It's that easy. Carbonite. Oh, Han Solo. Frozen in carbonite. Oh. Okay, I suck. I don't do Java very well. Anyway, well, what if it was an ion that had 2 less oxygens in the 8 form, or 1 less than the ite? All we do then is we put a prefix of hypo in front of it. Hypo means below in Latin, so we mean below the chlorite form. So this is hypochlorite. This is the ion below chlorite. I-T-E. Chlorite. That's not a D. It's a T. T. Hypochlorite. Okay? So if I were to name the sulfur and oxygen one that had only 2 in it, I would keep sulfite. Keep sulfite. And then say this is one below it, hyposulfite. How would I name CO2 negative? I don't think it exists. But how would I name it? It might, by the way. Don't quote me on that. Okay, this is, you can do this. It's one below the carbon. Hypo, right, one below. And I keep the same name. Carbonite! And that's it. It's that easy. What if it had 1 more oxygen than chlorate even has? Then we say another prefix called per, meaning more. Perchlorate. This has 1 more oxygen. Perchlorate. 1 more than the 8 form. Sulfur and 5 oxygens. I don't think exists, but in case it does, it'd be persulfate. Don't quote me on that. It might actually exist. And then if this had one more, it'd be a per as well. Percarbonate. Now, is it real important that you know these? I'm not sure that it's real important, but I do want you to know that there's a rhyme or reason to it. All right? It's going to be important when we talk about acids. Okay. All right. How do I write formulas of inorganics with polyatomics? It's really the same thing we just did before. It's no different. You just name the polyatomic ion in, okay? So, and you usually just look those up, all right? You usually use that common ion sheet I give you. Now, in the AP test, they won't have that for you. But, man, we're going to write so many of these, you're going to be so used to them, okay? So, what if I was given, like, NaNO3 to name, okay? Well, I recognize Na as a cation. That means NO3 must be my anion. And that's a common polyatomic ion you could look up. Okay? So I name my cation. That's a group 1 metal. It's only got one charge. I just say sodium. How do I know it's only got one charge? Group 1 metals only have one charge. Group 2 metals only have one charge. Most transitions have more than one charge. I gave you a sheet that has the ones that don't, like silver and zinc are common. Okay? That don't have more than one charge. So we wouldn't do Roman numerals for those. Okay? Only Roman numerals on transitions that have more than one charge, like iron, nickel, chromium, lead, things like that, manganese. Okay? So, you know, if you want to bet that the transition metal should have a Roman numeral, you're probably going to be safe. Silver and zinc are kind of like your exceptions to the rule. Okay? Anyway, so I wrote sodium here, no Roman numeral, and then I just named this polyatomic. Nitrate. How do I know that? I looked it up. That easy. Okay? What if I had Mn3PO4 taken twice? So much! Oh my gosh! All right. Manganese. Uh-oh, that's a transition metal. That can have more than one charge. So I better figure out what charge this is. Okay? So I should figure out what charge phosphate is. Because I could find the oxidation number that way. You might be like, oh, but before I did it for each individual atom. Well, I could treat a polyatomic ion together. Because I can look up phosphate to have 3 negative. Okay? I'll look it up. It's 3 negative. And I know I have 2 of these suckers. Right? So I know that 3 times whatever manganese has plus 2 phosphate negative 3 charges must add up to, well, let's see, the charge on this thing is Zippo, so it must add up to 0. So we've seen this before. X must be 2 plus. That means our manganese is 2 plus. So when I name this, I'm going to do manganese, dose, phosphate. That's all. No dyes, tries, or any of that. We don't need that. That's molecular. We don't do that. Okay? That's all we got to do, man. That's it. All right? Let's do one more for fun. Let's do AG 3 N. This might have some special organic name, but we're going to stick with it on inorganic terms, as an inorganic chemist would name it. Well, cation, silver. Now, silver is a transition metal, so go look. Does it have more than one charge? Do I ever write it with more than one charge? Does it ever look like I put Roman numerals on it on my sheet? Nope, sure don't. So I'm not going to do it. I'm not going to lie, I have seen silver with Roman numerals, so if you did write it, I really wouldn't grade you wrong on it, okay? But that doesn't mean, oh, I'll just do it every time. I mean, think about why you do it, okay? Silver. And then I have nitrogen, but this is the anion form, so this is nitride. Not a polyatomic, don't need to go look up anything. That's a monatomic nitride. And that's it, silver nitride. No polyatomic names to worry about. No Roman numerals to worry about. I don't have anything of that to worry about. All right? So, just remember, when you're doing inorganics, The metal, you name it first, then you name the anion. It could be a polyatomic. If it's a polyatomic, just name the polyatomic. If it's a monatomic anion, put the "ide" on the ending of it. Okay. If it's a metal with more than one charge, like one of the transition metals, seek out the Roman numeral by figuring out the oxidation numbers. Okay. There'll be more on oxidation numbers later, I promise. Okay. All right. I hope this helped out. Look at the other naming convention ones on acids naming, as well as look at the molecular naming video if you're having trouble with those. Okay? I'll see you guys later. Have a good one. Peace.